In the previous lesson, we explored the RBC user interface and learned how to define a simple free-running actuated controller and its associated detectors. In this section, we will learn to code a coordinated fixed-time controller with time-of-day plans and a semi-actuated controller with protected and permitted left turns. To model coordination in RBC, we will need to use patterns. We have already learned how to code a fixed-time signal with the vSim fixed-time controller. Let's learn to code a similar fixed-time controller with coordination in RBC. We will use the intersection in the west section of the network to code this fixed-time controller. The intersection consists of two through lanes and left turn bays on the major roads and shared through and left turn lanes on the eastbound and westbound approach. Let's take a look at the timing plan we intend to code. The timing plan consists of a 20-second split for protected left turns from major roads, a 30-second split for through movements on major roads, and a 25-second split for minor road traffic movements. Signal groups 1 and 5 refer to the major road left turns. Signal groups 2 and 6 refer to the major road through movements, and signal groups 4 and 8 refer to the minor road movements. The cycle length is 75 seconds. Yellow clearance is 3 seconds, and all red is 2 seconds. The offset refers to the start of green of the lead coordinated phase and is 15 seconds. Let's start by creating a new RBC signal controller using Signal Control Edit Controllers dialog from the menu. Let's first define the signal groups in the timing plan by selecting Basic Table from Base Timing, Timing by Signal Group. We define signal groups 1, 2, 4, 5, 6, and 8. Even though this is a fixed time controller, we will need to define both min green and max green for each signal group. Although we will set the signal groups to use their max green times for their general timing, the min green time is still necessary for offset seeking and some other situations, and therefore must be defined as well. Let's define the min green for all signal groups as 5 seconds. For max 1, we will use 15 seconds for signal groups 1 and 5, 25 seconds for signal groups 2 and 6, and 20 seconds for signal groups 4 and 8. Next, we will use 3 seconds for yellow clearance and 2 seconds of all red time for all signal groups. Since this timing plan has no detectors, we do not need vehicle extension time, but we will flag startup signal groups as 2 and 6. In the absence of detectors, as in this example, we will need to use recalls for the signal groups, otherwise they might get skipped in a cycle. There are two basic types of recall in RBC, max recall and min recall. Max recall places a call and extends the signal group to use maximum green time, whereas min recall only places a call on the signal group, resulting in it timing at least a minimum green. In case of a fixed time controller, we need the signal controller to use the maximum green time. Let's go ahead and check max recall for all signal groups in the timing plan. This way, all signal groups will use a fixed green time and are called every cycle. A basic timing plan without a pattern is always free running. In this example, we need our fixed time controller to be coordinated. To do this, we need to define at least one pattern in our signal timing plan. Select Pattern 1 from Base Timing, Patterns and Coordination, and enter splits of 20 seconds for signal groups 1 and 5, 30 seconds for signal groups 2 and 6, and 25 seconds for signal groups 4 and 8. Flag signal groups 2 and 6 as coordinated. Because we flagged all signal groups to max recall in basic timing, and since patterns inherit information from timing by signal group, there is no need to set signal groups in patterns to max recall again. Alternatively, you could have chosen to set signal groups to max recall in a pattern, but not in timing by signal group. Now that we have set coordination, we need to define the offset for the timing plan. Offset is a pattern-specific property in RBC. Each pattern can have a different offset. Pattern-specific properties are available in the box underneath the selection tree. The pattern properties shown here can be selected by double-clicking the intended pattern in the selection tree. Some of the other pattern-specific properties we will discuss in this section are cycle length and max green mode. The cycle length for our signal timing plan is 75 seconds. Max green mode allows you to set what max time is used in the pattern. There are 3 choices for max green mode: max 1, 2, or 3. In this example, we want the pattern 1 to choose max 1. Next, set the offset of the pattern to 15 seconds. In RBC, offset reference is a global property that applies to all the patterns. The offset reference definition usually depends on the type of controller being used. In our case, it refers to the start of green of the first coordinated phase. So let's choose lead green from the list. Another typical feature seen in signal timing plans is overlaps. Overlaps are signal groups that are defined as a combination of basic signal groups. The turn signal on an exclusive right turn lane is a typical application of overlaps. RBC allows up to a maximum of 16 overlaps. We will define overlaps for our minor street right turns. In this case, the right turn signal turns green with minor street through movement, and also when the non-conflicting left turn on a major street is green. Let's go ahead and choose Overlap Table from Base Timing Node and define 2 overlaps numbered 16 and 17. Overlap 16 is for westbound right turn. Overlap 17 is for eastbound right turn. To define basic overlaps, we need to define the parents. For overlap 16, the parents are signal groups 8, westbound through, and 1, northbound left turn. Again, multiple selections can be made in the list box using the Control key while clicking. Overlap 16 cannot time with signal group 5 because conflicting phase 2 can run concurrently with phase 5. Similarly, for overlap 17, the parents are signal groups 4 and 5. The yellow clearance and red clearance for overlaps are inherited from the parent signal groups and don't need to be defined unless alternative clearance times are needed. Other features of overlaps are for advanced applications and are not explained in this lesson. RBC allows you up to a maximum of 8 patterns per signal timing plan. This allows you to run different time-of-day plans in your simulation. Let's say we need a different timing plan for our peak hour traffic. During peak hour, our splits increase by 5 seconds for each movement, and our signal operates on a 90-second cycle length. In addition, the signal is coordinated to an offset value of 35 seconds, which is different from pattern 1. This can be defined easily in RBC using patterns and pattern schedule. First, we will have to force the pattern to use a different set of max green values. To do this, RBC allows users to use up to 3 different max green values: max 1, max 2, and max 3. Max 2 and max 3 are defined in the Advanced table under the Basic Timing by Signal Group node. For max 2, we define 20 seconds for signal groups 1 and 5, 30 seconds for signal groups 2 and 6, and 25 seconds for signal groups 4 and 8. Next, we will need to enter new splits to match our new cycle in pattern 2. Enter splits of 25 seconds for signal groups 1 and 5, 35 seconds for signal groups 2 and 6, and 30 seconds for signal groups 4 and 8. Again, flag phases 2 and 6 as coordinated phases. Finally, double-click on Pattern 2 and set the Pattern 2 properties to match our new cycle length, max green mode, and offset. Enter 90 seconds for cycle length and 35 seconds for offset. In Max Green Mode field, we will choose Max 2 to force all signal groups in Pattern 2 to use the Max 2 time we just defined in the Advanced Table in Timing by Signal Group node. Now that we have defined the signal groups, overlaps, and patterns, let's define the ring barrier configuration of signal groups in the sequence table. Let's choose the sequence table from the selection tree. In the sequence table, define signal groups 1, 2, and 4 on the first ring, and signal groups 5, 6, and 8 on the second ring. Next, place a barrier after the column containing signal groups 2 and 6 by clicking on the header of the second column. For the next step, we need to assign a start time for our patterns. Let's choose the pattern schedule table from the selection tree. By default, vSim defines a free-running pattern starting at time 0. We will change the schedule so that pattern 1 starts at time 0. We will then define pattern 2, which is our peak hour timing plan, to start at 600 seconds. We can also start a pattern at different times in a simulation. We create one more entry for pattern 1 to start at 2400 seconds. This completes the coordinated fixed-time signal timing with time-of-day plans. You will see a graphical timing plan in the panel below. Again, the timing plan shown here is of the pattern that is shown in the Pattern Properties box. You will see that the graphical timing plan changes by selection from Pattern 1 to Pattern 2. A graphical timing plan is shown even though a pattern is empty because patterns inherit information from timing by signal group. The splits of each signal group can be changed by dragging the signal group. If you want to avoid accidental changes, you can check the Lock the Diagram box. You can also see if there are any errors or warnings thrown by RBC. Let's confirm and save by clicking OK. In the resulting dialog box, enter file name as fixed time and save it in the same directory as the INP box. Click OK again to confirm changes in the vSim Signal Controller window and save the INP file. Similar to previous examples, we will place signal heads at the intersection and associate them with the fixed time controller and respective signal groups or overlaps. Let's start the simulation to view the intersection in operation. After configuring the signal times table, we will be able to view the details of the signal timing plan by selecting the Signal Controller 2 from Evaluations, Windows, Signal Times table. This time you will see that you can see the start and end green times of each of the signal groups. We can confirm the signal timing splits for each signal group by using the measuring tool in Signal Times table in single step mode. Finally, skipping forward to 600 seconds, we can also confirm if our signal timing plan has changed to Pattern 2 by measuring our splits. The Pattern 2 would then shift back to Pattern 1 after 2400 simulation seconds. Defining a semi-actuated signal timing plan is very similar to a fully actuated signal timing plan. The only difference being that the minor movements and left turns are actuated, whereas the major through movements are placed on max recall. Since this example is very similar to the fully actuated timing plan, we will only import the signal timing plan that has been already created. In this example, we will introduce you to the Import File feature in RBC. The Import File feature allows a user to import files into a RBC file and associate it with a new controller. Let's create a new signal controller using the Signal Control Edit Controllers dialog box and choose Edit Signal Groups. In the RBC user interface, select from File, Import File, and choose Import Example.rbc file from the dialog box. If you want to make further changes but do not want to override the import file, you can choose the File, Save File As option from the menu and rename the file. This is also needed if you import a file from a directory other than the one where the INP file exists. In our example, we will save it as protectedpermitted.rbc. In this timing, you will see that all the signal groups and vehicle detectors are already defined. You will notice the signal groups 2 and 6 are placed on max recall, and signal groups 3, 4, 7, and 8 are actuated. Signal groups 3 and 7 are protected left turn movements, and signal groups 4 and 8 are through, right, and permitted left turn movements. Let's associate this controller with this file by clicking OK. After defining the signal controller, we need to place signal heads at the intersection. Since we have already covered how to place signal heads, we will only cover the parts that are different from what we have learned. To define a protected permitted signal head, select Left Turn Signal Head on the west leg of the intersection. The signal head refers to signal group 3, which is the protected phase. A protected permitted signal head transitions from a protected to a permitted phase. To do this, we need to select left arrow as the signal type and check the or signal group box. In the resulting list, choose the west section through movement signal group, which is signal group 8. Hence, this signal will also show green when signal group 8 shows green. It is important to choose left arrow type for the signal head and not the circular type, since circular type may result in a transition that is not typical of protected permitted signal heads. Let's make a similar change to the signal head on the east leg of the intersection. Choose left arrow as the signal type and associate signal group 4 with the or signal group list. Let's start the simulation to view the intersection in operation. After configuring the signal times table, we will be able to view the details of the signal timing by selecting Signal Controller 3 from Evaluations, Windows, Signal Times Table. You will see that when the eastbound left turn receives a call, it starts in a protected mode and then transfers to a permitted mode. The signal head transitions from a green arrow to yellow arrow, followed by green block. Let's take a closer look at protected permitted operation in test mode at our intersection. You will see that when continuous calls are placed on detectors 3, 4, 7, and 8, signal groups 3 and 7 will first receive a green arrow followed by a yellow arrow indicating a protected phase. Thereafter, the signals are in permitted phase, which is indicated by green block for the left turns and have similar clearance intervals as the through movement signal groups. You will also see that if calls are removed from detectors 3 and 7, the protected phase is skipped and the movements start in permitted mode.